Again, good morning, good evening, good afternoon. Thank you for being here on the day 3 of your workshop for Python with AI for Pharmacometrics. So today is the last day of this workshop, and Dr. Datta is going to be covering the topics, and we also have a guest speaker, Nathan Teuscher. Dr. Teuscher, thank you for making the time to be here and sharing your knowledge with the team here.
You're
So,
welcome.
so without further ado, I will hand it over to Dr. Datta to get today's proceedings started. He will also walk you through on what is on the plan. A few logistics I wanted to share with you, which you have already seen in the emails that have come. There is a classroom which has been created. So please join the classroom if you have not already done so. And your homework assignments, the submission of the homework assignments, any questions that you have, you can post all of that in the classroom. And that is where we will be keeping track of any questions that come up. We will also be looking at your homework assignments. As you already know this, that we will actually be providing you a completion certificate, and the completion certificate will be provided only to those participants who have submitted all their homework assignments. The due date for having all homework assignments submitted is November 10th. The reason why we are giving you this extended time is because the fact that we have participants from 30 plus countries, so who have registered to the program. However, I'm also aware of the fact that for some of them, making to this classroom at this hour may not be feasible because it could be, some late hour for them. So the way we accommodate those participants is that we would record the session and we will post it on our YouTube channel. They also get access to all the slide deck, homework assignments, etc. So they can work on them at the time that works for them. So irrespective of the fact that even if they can't make it to this classroom, they will have access to all the material and also have access to the tutors and the teachers, so they can communicate with them online. All right. So with that, I'm going to hand it over.
Start over again. uh, okay, so today, as Arun has already mentioned, Dr. Teuscher will be covering covariate selection. But before I hand it over to him, I'm going to cover two specific topics. Well, one is a little bit about the homework 2 assignment, and the other one, which I will start now, is give you an overview of different packages in Python. So particularly those of you who have R background may have already noticed that in R, the packages tend to be somewhat more standard. There is one like what what functions you used for data frames and what you used for plotting is more or less the same. However, in Python, there is a lot of diversity. The user base comes from many different use cases. So usually you will find whether it is data frames or computation or writing a web app, there are several different packages to choose from. So what I'm going to do next in the next 5 minutes or so, I'm going to give you an overview of this landscape. Okay? So let me start with packages for computation and handling numeric arrays as such as vectors and matrices. We have already seen in our the examples so far that, well, NumPy, that is what we introduced in the very first class, and we continue to use it. It it remains as the most popular package for numeric computation. So NumPy has its own uh, data structure to store vectors and matrices, and as well as a large number of modules to do all sorts of math. And one good thing about NumPy is that the core of the engine is implemented in C++. So which means if you are doing math using NumPy, it is going to be a lot faster than if you had to do the same math manually, step by step. Like for example, if you wrote a loop in Python to add, a million numbers, it would be a lot slower than if you just called NumPy to add a vector of a million numbers. And so this way, even though you may have heard that, well, Python is a slower language than C, C++, but as long as you use one of these packages, you will see it is actually quite fast in practice. Okay. Now, NumPy is not the only package to store and do math with. There are several alternatives. For example, QPy, which has strong support, which has support for graphical processing units, GPUs, uh, which you know, which is NVIDIA's bread and butter. And QPy essentially makes it easier to work with CUDA. And then there are various machine learning libraries. You may have heard of many of these, JAX and PyTorch and TensorFlow. They have their own storage mechanisms. However, it turns out that NumPy is so popular that all the other packages that are here have their APIs very much compatible with NumPy, or if not 100%, like they would be almost 80 or 90% compatible with NumPy. And they will also have built-in conversion, because everybody expects that even if you use PyTorch or TensorFlow or something else, you might be frequently converting back and forth with NumPy because people are just very familiar with NumPy. Okay. Next, let's talk about data frames. So previously, I was just talking about numeric vectors and matrices, but data frames, as you all know, it's basically a table with columns, which can be numbers or strings. The most popular data frame package is pandas. However, there have been faster other alternatives. One of the notable ones that have become somewhat popular recently is polars. It is for a lot of operations, it is noticeably faster than pandas. And lastly, even though many people are comfortable doing SIG operations like filtering and merging and joining with data frames, there are many who come from the SQL world. SQL, is a query language used to operate with data that is stored in databases. And they often find that they are very familiar with the syntax of SQL. And because data frames kind of do the same things, so why not have packages that actually uses the SQL-like query language? So to serve that, you also have packages like SQLite and DuckDB, which basically means your data or your table is stored in memory data frame, and you can actually query it with an SQL-like language. Okay. Next, let's talk about plotting. So unlike R, where ggplot2 is like very universally popular, in Python, the loyalties are kind of divided. So matplotlib continues to be what you would might call the basic plotting package of Python. And in fact, if you open a pandas data frame and call dataframe.plot, it behind the scene, it actually calls matplotlib. Matplotlib is very comprehensive, covers all sorts of things, and gives you a lot of power to change minutely things that you want to. One of the alternatives to matplotlib is Seaborn. It is quite popular with stats people, and one of the good things about Seaborn is that with very few commands, it gives you a very nice looking plot. Like unlike Matplotlib, where the basic plot is very drab and not uh, it's very lackluster. And if you're want to make it look nice, you have to select your own colors and styles and things like that. Whereas Seaborn by default has a very nice looking look and feel basically. So for example, I will show you here. Here is an example of a basic Seaborn plot. The default color palette is already very pleasing, and the selection of the the styling. Another alternative is Plotly. So the speciality about Plotly is it is a bit more interactive. So for example, things like things appearing on hover is kind of first class. You can make that work with very little. It's almost by default. Like if you can see the command over here, all you have to do is just mention which column of the data frame should be used for hover data. And in fact, that is just extra hover data. You didn't have to do that. Hover kind of comes by itself. Similarly, many other interactive elements about making certain lines pop and things like that are a lot easier with Plotly. Uh, and similarly, there are other packages like Bokeh and Altair, which are also interactive like Plotly. And the last one I will mention is Plot9. It's not that popular otherwise, except for people who are coming from R, because Plot9 is literally a ggplot2 clone. So whatever you can do with ggplot2 in R, if you love that syntax and you don't want to learn something else, you can use Plot9 in Python. So that is about plotting. And the last one I will mention is how to write web apps. So in R, Shiny is very popular. In Python, these are some of the main web app packages or frameworks. Plotly Dash is, well, it comes from the same people who wrote Plotly. And Dash allows you to write more callbacks and things that can happen when you click or hover. So if your web application is very much plot heavy, Plotly Dash is a great alternative. Streamlit is another alternative. In fact, Streamlit is very popular for writing chatbots. And both Plotly and Streamlit are also, they have a very simple interface with very few lines. You can create an app. And Django and Flask are frameworks which do more than just front end. They have a very strong integration uh, about connecting with your backend tables and databases and APIs. So that's kind of the very high level overview of the package landscape in Python. And we will be sharing this slide deck with you, so you will have access to this. The last slide here just connects links to the notebook that Dr. Teuscher will be talking about with covariate selection. So you will have access to that right from here. But before we go there, is there any questions I can address before I jump to homework 2? All right, so I'm going to go into homework 2. And also, I will request you that this is because this is the last class, so feel free to ask anything and everything that is in your mind. We'll try to address them. And of course, afterwards also you can put your questions in the Google Classroom. So let me now go back to homework 2. Actually, so if you recall in homework 2, what we had done is we had first introduced you to a data frame which has a lot of bunch of different information about. It has time and concentration details about some 20 or so patients, actually maybe more. But it also has data about the patients like age, sex, height, weight, etc., and the sequence. And so the idea here was instead of just trying to predict from one input variable, can I see how random forest can work with multiple input variables like 8 or 10 in this particular case. Now, so the way we did that is In fact, what we did in week 2 lecture is we just defined the question. In fact, we wrote a prompt like this: split the data frame into two halves, train a random forest model with the first half, and predict the concentration column, and then validate it. So we actually just wrote this prompt and simply asked Gemini to write the code, and it wrote a code. It took a few iterations, a few things failed, and eventually it wrote a code that kind of does the job. And homework 2 was to just clean it up, refine it, and do your own experimentations with it. Uh, in week 2, I had left it a little bit open-ended. So what I've done here is I have done a little bit of cleanup myself, and I will be sharing this sheet. I'll put the link in the same slideshow. In fact, I will put it in the week 2 slideshow. So I'm just going to show a few more things that I updated here. So one of the first things that you would have, or that AI version of the code did, is it took the data frame and it divided the number of rows, and based on that, it created two halves, half one and half two. So the first one it would have used for training, and the second one it would use for validation. Okay. Is here the train output from the training half, the concentration column is the output, and everything else, if you just drop the, was the X data. And when it first tried to use that, it failed because there was a lot of data here which was string, which is not going to be able, the curve fit is, or rather random forest would require a numeric output. So you have to do something about it. And there were two ways it handled the string data. One way was to just drop the data. So certain things like patient code, food status, and sequence, it just decided to drop altogether. Don't use it. The other ways, for example, sex is also a new string column, but instead of dropping it, what it did is it converted into a categorical data, which the random forest model is about to is able to handle. In fact, in this case, it's just a two-value categorical model. Right? So with that, it proceeded to train the model. Training was fairly simple. All it needed to do is just call the random forest regressor, and basically that's it. You don't really need to define any model or anything, only some parameters like number of estimators and things like that. Once you have the model, it is able to produce predictions from a new set of X data too. So that is the second part. So the way it ended up validating is use the trained model to predict using the text test data. So this is the data that is coming from the second half of your data set. And you got the prediction. Now we also happen to have the actual values from that second half of the data set, which is Y test. And just to find out how well the model did, what it did here is just calculated the R-square score from the Y test and from the predicted Ys and the original Ys. It so happened here, R-square value here was negative 0.2, which is pretty bad. It practically means, there is no, in fact, negative correlation between your prediction and your original data. So we'll look at it a little bit more further down, because this may not be the only way to look at how well your data fits. The code above so far has been mostly the AI generated code, which I cleaned up a little bit. I removed the trial and error part and just kept the part that works. Below, what I have done here is I've tried to do a few more things to slice and dice, try to understand this particular data. So here what I'm doing is I'm just grouping by patient code. The original data had some 1,000+ rows, right? Multiple concentration for each patient. So here I just group by the patient code just to see how many patients are there and what is the distribution like by age, sex, height, and weight. that is being done here. So it looks like there are about 60 patients. Next, I'm just plotting the predicted Y and the original Y. And well, we had already seen the R square, which was negative 0.2. So clearly, as you can see here, that looks very much all over the place. The prediction looks quite horrible. Now, what I've done here is I have taken the second half of the data, this DF half 2, and just created a second column called concentration predicted using what we just got from the model. So this is the data. This last column is created from the model. And so this is the predicted concentration, and here we also have the original concentration. And the reason why I did this is because I was not happy with just looking at the R square and just this and this. I wanted to be able to look at the data a little bit more, and what I mean by that, we'll see just below. So just scroll down quickly. So what I did here is actually what I write here from DF half 2 only use patient code 61. Let's just pick on one patient code and let's just plot the line concentration versus time and another line concentration predicted versus time. Uh, in fact, what I had actually done is I used this comment as a prompt, used ChatGPT to produce this code. Just to illustrate that you don't really need to know your syntax accurately. Having said that, you still need to have some idea because ChatGPT often, or any other AI tool that you might be using, it doesn't work 90%, 100% of the time. It will often make mistakes. So you still need to be able to browse through it and see, oh, is it really doing the right thing? Okay. Okay. So in this case, I just use one patient code and I'm trying to see the concentration versus time plot from the original data versus what was predicted using the model. And so here are the two. So here it doesn't look that horrible as we previously thought from the R square. And what we do here is basically the same thing, except I'm doing it in a loop. If you recall from the last class, we are able to do what I think in our world is called faceting. We are able to do multiple plots arranged in a grid, which is plot command in matplotlib. And in each plot, I think there are more than 30 patients. We just took the first 9 unique patients in the test data. Actually, we did it here. Get the first 9 unique patient codes. And for each of those patient codes, we just, whatever we did just before, for each patient, plot the prediction and the original separately. So that's what we did below. So this code inside this for loop is just what you saw before. And here is what we got, observed concentration versus the prediction. This is just me being that, hey, I don't know if the R square is giving me a true picture. So let me try to look at the data in many different ways. And what you guys can do is, I will share this sheet, of course, and then you can take it from there and see what else you could do. You might have other ways of looking at the data. One of the things you will find that one of the difficulties here is there were like 5 or 6 columns: age, sex, height, weight, BMI. And we are trying to make the model use all of that and to predict. Do we really need all of them? Is some of them like spurious, some of them maybe is misleading, or maybe there is duplicated data between some of them. So you may need to figure out which data you really want to use to train. And actually that is where the next topic comes in. What Dr. Teuscher is going to talk more about is covariate selection, is like trying to understand what part of what part of the input might be actually related or might be thrown out, and what we want to keep or not use while we train our model, right? So with that note, I'm going to stop here. And yeah, feel free to ask any questions. And actually, I'm going to stop sharing. Dr. Teuscher is going to pick up from here.
All right. Any questions for Sandeep? I don't see any hands popping up. So, hello, everyone. I'm going to talk about one use of machine learning for pharmacometric analysis. And this is my name. I call it the Boruta method for covariate selection. Maybe that's not very original, but it's applying the Boruta method to covariate selection. So covariate analysis in PopPK can be very time consuming because of all the models that have to be run. So there's two general approaches that are taken for covariate selection. One is a stepwise search process. And the second is what's called a full model, where you include all of the covariates up front. And they both have drawbacks. Now, the drawback of the stepwise addition is that it's slow. So if you have 20 potential covariate parameter relationships at the beginning, that means you have to run 20 models simultaneously. And then the next round, you run 19, and then 18, and then 17, and so on until you get to your final model with everything added in. In addition, there is some bias that's involved in the stepwise addition, because as soon as you add the first covariate, that could bias which covariate gets added next. And so although there's issues with the stepwise addition and backwards deletion process, it's the most common method used for covariate addition. Now, the other option is the full model. So full model is you include all the covariates, all the 20 covariate parameter relationships up front, and you run one model, and it sounds great. The problem with it is, in my experience, 99 out of 100 full models fail. They don't minimize, and so you don't have an answer. And so the solution is you start removing some of the covariate parameter relationships until you get a model that minimizes. The issue with that is you're biasing the results, because again, you're removing what you think might be causing a problem in the statistics, but you don't really know, and there's no good way to test it. So there's many variations around each of these that attempts to resolve these issues, and they're all fine. I found this Boruta method is extremely fast and extremely efficient, and so that's what I'll kind of walk you through today, what that is. So I'm going to share my screen here. If I can find the right button. Okay, so this is just the notebook that is shared. So you should have access to this, and you can go through it. It has the code here, and I'm not going to run the code, but I will kind of walk through it. So the basic process is, it's two steps. You're going to use machine learning in this Boruta method to select the likely covariate parameter relationships. And then once all of those are selected, you're going to include them in one model, and you're going to run that one model. So it's sort of a mixture of these two processes. You are doing a selection process to get the most likely covariates up front, but then you're running them all as once instead of a stepwise fashion. And so it's kind of like the full model approach. So in my estimation, it's a little bit the best of both worlds, because you still only have to run one model, like the full model approach, but you don't have the bias of removing things sort of arbitrarily based on what you think is going to work. So the Boruta method to identify these covariate parameter relationships uses a couple tools, and one that Sandeep has already told you about. So the first is it uses a random forest regressor to identify or prioritize relationships between covariates and parameter estimates. The only challenge with random forest is random forest just tells you whether one thing is more likely related to the output variable than another thing. It doesn't tell you if it's statistically significant or not. It just says this is more likely than that. What we want to know is, well, not only which one is more likely, but is that more likely actually possibly statistically relevant? And this is where the Boruta method comes in and does that. And I'll kind of explain that in a second here, how that's done. So it's going to do a random forest, and then it's going to implement a statistical test to see if the most important things are statistically significant, and then give you a likelihood that there's a correlation between a parameter and a covariate. And then we run this through all the different covariate parameter relationships, and then we have a list of likely covariates that we can include in the final model. So let me kind of show you the code of how this works. So the packages, as we were talking about, there's sklearn. There's a random forest regressor, and I think I saw in Sandeep's code this. He used this previously. There is a package called Boruta Pi. And so you need that package. That's the only unique package. And then you need pandas and numpy. So both of those you've probably used before and have experience with. So this only new one is this Boruta Pi. And this is specific to this Boruta method. So you're going to import your data. So I use, in the example, I used a non-mem output file. You can use any modeling software you want. What you need is not only covariates, but you need the parameters, the individual parameters that you want to test. Now, an important aspect of this is, if at all possible, you want to include inter-individual variability on each parameter for which you want to test covariates. If you don't have an IIV, then everybody gets the same parameter. So if you don't have an IIV on Ka, everybody has the same Ka. So you can't really draw any relationships between Ka and covariates because everybody has the same thing. So if possible, include IIVs on everything for which you want to test covariates. It might result in a model that is not as stable because sometimes the IIV is not estimated very well, and it may have a high shrinkage. That's okay. It's better to try it than not. So you can see we have all of these things. I have subject ID, and then I have my set of potential covariates, and then I have my PK parameters here at the end. So that's it. And then I want to, usually non-mem data, there's multiple records because you have multiple concentrations. So I limit it down to essentially one row per subject. So now we're going to start the Boruta method, and we do it one cycle of Boruta for each PK parameter. So we're going to start with clearance. And I'm not going to, the code's actually documented reasonably well, I think. If you have questions about it, you can stop me. Feel free to stop me while I'm talking. But essentially, we're going to set up a random forest regressor. So that's what this line does. It sets up this thing called a model, which is a random forest regressor with 500 estimators, a maximum depth of 5, and a random state of 42. And then we set up a function called the feature selection with this Boruta Pi. And everything is left normal. The only things I would recommend changing is your maximum iterations. So the default is 100. Sometimes you might want to try 200 more iterations, and I'll explain what the iterations are in a second. And then you need your alpha level. So the default is 0.05. I actually prefer 0.01. So 0.01 says that this is your alpha level, or the likelihood that you're going to select something that's not really related. I only want strong covariate parameter relationships, so I'm going to choose 0.01. If I wanted to include weak covariate parameter relationships, I could include 0.05. So it's up to you. I prefer 0.01, but 0.05 is fine. I would not include 0.001, which is a normal alpha level for backwards deletion. I would not include that. I think it's too stringent. So we have our feature selection set up, and then now this is where it's going to start the work. So the first thing is I get a vector y that has the clearance values, and then I get a vector x which has all of the covariates that I want to test against that parameter. And then I'm going to run this feature selection fit on these two arrays, an x and y. So what it actually does is the first thing it does is it runs a random forest, and it prioritizes the which of these covariates is the strongest predictor of clearance, and then which is the next strongest, and the next strongest, and the next strongest. So it just prioritizes them. That's what a random forest does. And then the magic in the Boruta method is this next step. And what it does is, let's say weight is the strongest predictor of clearance. It creates 500 new data sets of weight and clearance by randomly scrambling the weights amongst those clearances. So for example, let's say you have 50 subjects in the data set. So you have 50 clearances and 50 body weights. It'll create 500 new data sets with the actual weights, but they're randomized amongst all the clearances. So these are fake data sets. It's 500 fake data sets of randomly assigned weights to clearance. Then it does a regression of clearance and weight. And it says how likely is it takes the best correlation between clearance and weight from those random data sets, and that says how much better is the correlation between the actual weight and clearance. And if that correlation is better than 0.01 alpha level, it's significant at 0.01 alpha level, then it says, weight must be related or is likely related. It's not a random event. So essentially it's saying is the actual weight correlation with clearance statistically significant relative to a random distribution of weights. And then it does that for all of the covariates. So essentially you get a selection of confirmed. Tentative means it's right on the borderline, so it's going to keep testing it. That's what these iterations are for. And then rejected is it's not. And so you get your results, and you get a listing of those. And all this does down here is show you a listing of it. So I'm going to scroll down. So we ran clearance with all these. It finished, and there were 0 confirmed, 0 tentative, and all 10 were rejected. So none of these were statistically significant. So ALT had the strongest relationship with clearance, but it was not statistically significant. And sex had the weakest relationship with clearance. But again, none of them were statistically significant. So basically it's saying none of these covariates appear to be related with clearance. So now you can try the next parameter, and it's virtually the same thing. We're going to take our volume of distribution of the central compartment and then all of our covariates, and then we run our feature selection, and then we summarize the results. All of this code is the same. The only thing that changed was this one line right here where we input a new parameter. If we look here, again, volume, none were confirmed and all were rejected. So again, we have nothing that's statistically significant. If we move on to the intercompartmental clearance, I think this one we get 1 confirmed and 9 are rejected. So it looks like age is likely correlated with our intercompartmental clearance. And then we run it again for the peripheral volume of distribution, and we get body weight as a potential covariate on the peripheral compartment volume of distribution. And then the last one is Ka. So we run that again, and we found that body weight was a potential covariate on Ka. So our final results of the Boruta approach is there's 3 potential covariates that we would include in the model. age on intercompartmental clearance, weight on peripheral volume, and weight on Ka. So this actual code here, it takes maybe a minute to run all of this code. So you're running through a selection of covariates. It takes a minute. It takes you longer to type it up and edit the code than it does for it to actually run. So you're going to spend maybe 15 minutes doing covariate selection. Now you have your 3 covariates. You put these in a model, and then you run your population PK model using whatever software you're using, non-mem, NLMXR, Monolix, whatever it is. And then you're going to get an estimate of these effects. Now, these effects might not be statistically significant when you run your model. That's okay. All this is saying is these are likely or possibly related as covariates. If they're not statistically significant in the pop PK model, it says, let's say age on intercompartmental clearance. Let's say that's not significant. Then you could say, well, maybe I don't have enough data to show an effect, but there's a possibility that it might be related. So we want to keep an eye on this in future clinical studies. The same thing with weight. It's maybe it doesn't show an effect. It's not statistically significant, but it's something that we want to keep an eye on. And so this makes it much faster to do your covariate selection because you take 15 minutes to run it in Python, and then you run one model, and then you have your results after that model's done. When you have model runs that take 8, 12, 24 hours to minimize or longer, this is a huge time savings for you because rather than running for 7 or 8 weeks, you can get it done in a day or 2. So that's kind of the end here. You can you should be able to run this code. If you want to test your own data set, all you have to do is come up here, import your data set, okay, and then identify the covariates and the parameters in your model, and then you change those covariates and parameters down here in these sections, and then you can run yours and see what you get. I've done this on multiple population PK analyses, and I have always, so we ran it on 5 different models, and we did the forward selection, backwards deletion process, and this. In every case, every covariate that was picked up as a final covariate in the forward selection, backwards deletion was absolutely picked up with the Boruta method. There were almost always extra covariates that showed up in the Boruta method that we included, but they often were not statistically significant covariates. So they were included in this sort of full model, I'll call it, but they didn't end up being statistically significant. So in the end, we got virtually the same covariate models, but it was much faster and easier to do. So I'll kind of stop and see if there's questions about this or some details that I can kind of address. I don't know if I see there's hands, or do people just unmute and there you go. Go ahead. Do I have to?
Good morning, Dr. Nathan. So thank you for your explanation regarding covariate selection and all. So actually, I've been using non-mem actually. So for this covariates, actually, if I use non-mem, this forward addition and backward elimination process, I have to develop nearly 30 models.
Yes.
So yeah, more than 30 models I need to develop. But simply with this Boruta method, so based on the number of covariates, number of parameters, so that models are enough. So I do have a couple of questions here.
Mm-hmm.
So in the selection of a data set, so you mentioned that individual parameters also we can include, like, you mentioned database, the clearance, individual clearance or individual volume. So is it the population values or individual values also we can include? That is the number one. And number two, so regarding actually in the forward addition, backward elimination in the non-mem, so typically we use the chi-square test to reduce the models, the statistically significant and all. But here, so how we can this directly it is showing directly, so this is the actual correlation is there or not, like that. So which statistical test it is using here, that is in order to select the perfect covariate model on that particular parameters, and that is the second one. So
Okay.
yeah.
Oh, was there a third one, or can I answer the first two and then I can get the third one
Please,
after?
please go ahead. Thank you so much.
Yep. So the first question, the correlation is between the individual parameter and the covariates. So you have to have the individual parameters in order to do this method. So that's why I was saying if you didn't have an IIV on KA, it would be everybody would have the same KA. So it really wouldn't be able to do a correlation. So you have to have the individual parameter estimates for all the subjects for the parameters you wanted to test. If V3 is you can't fit it with an IIV, the model won't ever fit. That's fine. Don't include V3 in your search. So that's the first question. The second question is around what statistical test. So the chi-squared test is used to compare objective function values for two nonlinear mixed effects models.
Yes.
In this case, we're not comparing a model fit. What we're doing is looking for a correlation between a covariate weight and a parameter clearance. So it simply uses a linear regression to compare them. I'm not entirely sure that it's only linear, because you could have nonlinear relationships between parameters and covariates. That could possibly happen. But I think it does a linear regression test to evaluate it. So it's looking at hey, a linear regression is to sort of prioritize what's better or not. You may be able to adjust that in the Boruta, but I haven't tested it. I haven't needed to try it, because again, I'm just looking for a correlation between a covariate and a parameter. That's all I'm looking for. And so I think linear is usually good enough in most cases. So that's how that's done there. Now you can, after you run the full model. So this in this example, there were three new parameters, and you can use the chi-squared test with degrees of freedom of 3 and look at the objective function value between the base model with no covariates and the full model with 3 covariates, and you can look to see if that's statistically significant. So you can still use the chi-squared to compare your before and after models to each other. You just have to make sure the degrees of freedom are appropriate for the number of covariates you've added or number of parameters that you've added to the model. Did that answer both of those questions?
Yeah. So thank you, Dr. Nathan, for explanation, and also it is pretty clear. And instead of using this forward addition and backward elimination taking so lot of time, so we can, if you use the Boruta method, so it is easy to implement and all. So one more last question. So is it approved by regulatory bodies, that Boruta method and all?
Regulators don't approve methods. They review analyses and provide feedback. I have used this method for covariate selection for drugs that have been submitted to, global regulatory agencies, and I've never had any concerns with it. So
thank you.
they won't publish and say, we approve this method, but I've used it and we've submitted and they've had no concerns.
Thank you, Dr. Nathan. Thank you so much.
Yep. So there was a poster that at the PAGE meeting, 6 years ago or so. I'm trying to remember when it was. Maybe it was 2021. or 2020. I'm trying to remember. It's a fog with all the shutdowns with COVID. I don't remember the year. But we did do a poster on it. So if you want a reference for it, you can look up the PAGE meeting, which is the Population Analysis Group in Europe, and look for a poster with my name on it. I was one of the corresponding authors. And you can see they did a comparison of the different methods, including the forward and backward addition and the Boruta and the accuracy of them.
Thank you, Dr. Nathan. Thank you so much. So I will go through the page and I'll help.
Go ahead.
I have a question. So if we have a highly correlating covariates, so do we still include those correlating covariates in the analysis, or how do we approach the situation?
That is a great question. You can still include them in the Boruta method. Highly correlated covariates will not cause a problem for the Boruta method. So in particular, it will help because it will, using the random forest regression, it'll prioritize, let's just take an example, body weight and BMI. Those are very highly correlated, right? You could include both of them. It's going to prioritize body weight or BMI higher for a relationship. And so Boruta is not going to be impacted by highly correlated covariates. Now, if it selects both body weight and BMI as potential covariates, you might have to, in your full model, you might want to select just the strongest one based on the priority that comes up. So let me scroll down. When you get a ranking, right? And a lower ranking means higher priority. So if body weight is here, and if, let's say, BMI was up here and they were both green checks, I would actually use BMI and not body weight. But you could also try including both in the model. They might include non-overlapping information. So correlated covariates only impact the nonlinear mixed effects model. They don't impact the Boruta method. Did that answer your question?
Yes, thank you. Thank you so much for the answer.
What I wanted to do, Nathan, is I wanted to ask you for your opinion on a few more things. So one is, earlier in the call, I talked about various Python packages. These are more generic packages, right? But I wanted to ask you about your experience on pharmacometrics specific packages. What is out there? And things like different kind of analysis, non-mem, population.
Yeah, so I will say there's, gosh, now I'm not remembering the specific packages. I'll have to rack my brain and see. So the Boruta method is one for covariate. That's they do have an implementation in R, but it's not as easy to use, and it's definitely not as fast as Python is. So so definitely the Boruta is one that's it's preferable in Python. The other that is it's, I think you mentioned it, SciPy, I think is what it's called. So there's I'm not aware of a nonlinear mixed effects modeling package in Python, but there is a model fitting. So if you do an individual model fit, you can do that with SciPy. And so you can do that to quickly do fits of individual profiles, and that can give you initial estimates perhaps for a population model. So my use of Python has been restricted to the Boruta method that I showed you, and doing SciPy for individual model fits. And then I use plot9 for plotting, and exactly why Sandeep said, hey, if you come from ggplot world, plot9 is great because it's all the same. And so I use plot9 as well for plotting, and because it's just easier for me to remember how to do the code. So I think those are the three packages. Maybe others are aware of a nonlinear mixed effects package in Python, but I'm not, but I haven't looked very hard.
So now that you talked about your own usage, can you tell a little bit more about how you decide I'm going to do this in R versus I'm going to do this in Python?
So my default is R because that's where I produce most of my outputs in R. So I produce, I do tabular summaries, I do data manipulation, and I do that in R, and that's historical. I definitely use Python for any of the covariate work. And so it's fast and easy, and I come over to Python and I do that specifically in Python. It's sort of what I'm doing. Now I will say I use Python in another context. We have some software that we've developed, and we use Python on the back end for that because it's significantly faster than an R instance for software purposes. And it's easier to code than something like C# or something like that. So we use Python in our software development for non-compartmental analysis. We use Python for individual model fitting and plotting and table creation. So all that we use Python in our software development activities. But that's not really that's not necessarily pharmacometrics, but because we don't expose that code to others in Python, we have a packaged software that we provide.
Actually, can you tell us a little bit more about your software, like what it does and why you developed
Yeah,
it?
so it's the company is called Aplos Analytics, APLOS Analytics, and our software is Aplos NCA. So it's a web-based API for calculating non-compartmental parameters. So it's accessible through Python code, through R code, SAS code. We also have a web interface that you could use. If you really want a point and click experience, you can go to our web interface. But what's beautiful about it is you can access it from a programming language you're already using. And all you have to do is send it data, and then you send it instructions for the NCA analysis, and then it calculates the PK parameters, tells you it's done, and then you download a package of results. And so you could integrate it into an R script, for example. And you could so you could do something like let's say you had a single ascending and multiple ascending dose study, and you have to analyze the data at each cohort, and then you want to run a dose proportionality assessment. So you got 3 cohorts done in single ascending dose. You can send the data up, get the NCA parameters back, and run a really quick power model for dose proportionality right in R, and you never have to leave R, and your parameters are calculated and robust. And then if the statistics group wants to create a table for a DMC or a data monitoring committee or something, you can send them the package of results, or they can just access it through SAS, and then they can pull down those results and summarize. So it's a nice package. Some people are actually using it for initial estimates. So you send your full profiles up for your pop PK model. You parse it down to just full profiles, send it out for NCA, get the results. You summarize clearance and volume and Ka parameter, or sorry, clearance and volume parameters, and then use those as your initial estimates in your population PK model. It's very fast. It takes about 1 second per unique profile. So if you have 50 subjects, it's going to take less than a minute to get all your results back. And so it's very fast and efficient. So if somebody's interested, it's free for academics, but we also give free trials out if you're interested.
Yeah, that sounds good. So if somebody is interested, yeah, you can reach out to. You have your website, right? And of course,
Yep.
you can also reach out to us, and we will connect you. Right? Your sheet.
I have it up. Do you want me to share it from my screen?
Okay, sure. You can do that. That is great.
And then you can tell me where to go.
Yeah, one
You
was
can
just
make fun of my bad my bad Python coding habits because I'm an R coder.
well, you've written And actually, Notebook gives you the choice to both either write as text in the notebook or as comments.
Yep.
So actually, one comment was for those who are going to be working on the homeworks, particularly homework 2, because it's kind of open-ended. And I would say, even if you try something and it doesn't work, do please still submit and make sure that in your comments you have explained what you were trying to do. That makes it easier for me to understand what you were trying to do, and maybe I could help. So yeah, for homework 2, do still submit and make sure you explain what you're going to do in the comments. Here, one of the things I wanted to people have pay attention to is pip install Boruta. So one of the reason why I may have covered it in lecture 1, but what happens is that in Python, any package you need, it has to be installed in whichever environment you're running it in, whether it's your computer or whether it's the cloud environment. Now, in your computer, you usually have to install everything, sklearn, pandas, numpy, and then you can import. But what happens in Google Colab is Colab, to make it easy for you, already pre-installs most of the popular packages. So you don't actually have to pip install pandas and numpy. You just have to import. But packages which are not that universal, like say Boruta, which is more specialized, you will have to pip install. So that is one thing I wanted to note. And the other, Nathan, can you scroll down to an instance of use of f strings? I think somewhere down below you used f strings. And
Here?
oh, right there. Yeah, right there. Right. Yeah, that is one.
Oh, so something like this.
Something like this. And I have also used, but I never talked about it. This is a little bit of a unique feature. And in Python, there are several different ways of formatting your print. But over time, f string has been it has kind of emerged as a standard. So you can call this is now the recommended way of formatting your code. And what it really means is just by adding an F in front of the quotes, you have made sure that inside the quotes, you can also have things which are just not string, but also variables. So here you will see that the feature is actually a variable and put it in curly brackets. So it's going to print whatever is the value of the feature. And you can also add formatting commands. So for example, if it was a number and you wanted to make sure it's printed using whatever decimal places, so there is a way to do that. So again, I'm not going to go deep into the syntax here, but just wanted to mention that you might find some users use other ways of formatting their print, but f string is considered as the recommended style. All right, so I will just end here. So if there are no other questions, yeah, we'll just end 20 minutes early.
There's one hand up. I just saw one hand pop up.
Sorry to disturb you so much. So, one last question, Dr. Nathan. So regarding this Boruta method, so how do we evaluate the model? I mean, the model diagnostics and all. So, can you please provide some light on that?
No different. So there's no. I mean, when you're saying evaluate these diagnostics here of the Boruta approach, is that what you're asking?
Yes.
Yeah. So it's basically going to. It's going to bin. Boruta is going to bin it into 3 categories. Each feature. So a feature is your covariate, and it's either going to confirm that it's related. It might be in the tentative, or it'll put it in rejected and say it's not related. Essentially, if it's confirmed, that means that the relationship between the feature and your parameter is statistically significant at the alpha level that you set. In my case, 0.01.
Okay.
If it's tentative, and this is one I'm not entirely clear on, tentative means it's right on the borderline. So if your p is 0.0 or your alpha is 0.01, maybe it's 0.012 or 0.015, right? So tentative sort of says, maybe it's right on the borderline. Rejected means that the p-value it's not related. So, and then this is just an individual listing of all the features. So, and the ranking means which one was the lowest ranking means the closest or the best correlation with the parameter. So this is sort of ordered from most related to least related down here. That's it. That's all you have to kind of review. When you do your actual model with the covariates, you would review that just like you would any population PK model. So you'd use the same diagnostics of, diagnostic plots and parameter estimates and everything you would normally look at for a model. But yeah, this is basically what I look at is what's confirmed, tentative, and rejected. And you can actually, if you go through and change this code up here, let me find where I do it. Right here. So try changing this to 0.1 and just rerunning the code. And you'll find that there's more covariate relationships that are significant at the 0.1 level compared to 0.01. And so you can try changing this and see how it impacts the results. Did that answer your question?
Yeah. Thank you.
Yeah,
Dr.
you're welcome.
Thank you.
So actually,
And
that
one more
gives me
question regarding this homework, Somdeep. So is there any specific format that we need to share, or simply PowerPoint is enough?
well, I think at least for me, the easiest format is you work on a collab, right?
Yeah.
Basically, when you copy the collab notebook, well, usually because you don't have write permission, it will create a copy. All you need to do is just take the link of that notebook and drop it when you turn in your assignment.
Sure.
So that is the easiest for me, because
Yeah, actually I prepared a presentation, so, and also I copy that link and I pasted. So I copied the collab, all scripts and all, and I pasted, and just wanted to share that entire for the PowerPoint presentation. So
that's
okay?
great. Yeah, if you have a PowerPoint, that's great. But otherwise, you could also just write your notes and explanations in the notebook itself, because it offers you a lot of formatting capabilities.
Thank you, Dr.
And so just because you broached the topic of the homework, I had left it very much open-ended, right? You could do different things. You could, in fact, apply the Boruta method that you just learned today into that homework too as well, because there also we have got multiple variables. And so where I'm looking to see some experimentation is in how you modify the modeling, it could be selecting variables. And the other is how you view the results. Did I get the right thing? Like, as you saw, you could see R-square, you could see different plots, and just from the validation questions, like how do you satisfy yourself that you got something reasonable, and which becomes more of an art, right? That did I pick the right variables? So in fact, Nathan, I have one question for you. I was thinking about what you spoke about the regulators. So what you said is the regulators were okay with Boruta. Is it fair to say that the regulators don't care as much about how you pick the covariates, as long as you can demonstrate that your results are reasonable?
Yes. So they're looking for scientific, rigor. And this is a method this is one method of covariate selection that has advantages and disadvantages. The disadvantages, the advantages, it's fast, it's efficient, easy to do, saves a lot of compute time. The disadvantage is you can't test covariates on parameters that don't have between subject variability estimates. So if you don't have an IIV on a parameter, you can't test a covariate. With the forward addition, backwards deletion, or the full model approach, you just stick it in there. Now, if you can't estimate an IIV on a parameter, why would you be testing a covariate is a question I would ask. But that is a downside of this method. So, but every method has pros and cons and limitations. Just understand that's a limitation of this method. So yeah, as long as you explain the method you used to get where you got, and you can show that the model accurately reflects the observed data, regulators are fine with it.
Right. So I think we will now close here. Any last comments from you, Nathan?
No, thank you all for joining. And Sandeep, thank you for inviting me. Python's sort of a new area for pharmacometrics, but it is very valuable for some of these machine learning tools. It's much more efficient than anything else. So thank you for inviting me and letting me share.
Thank you. Thank you for sharing your wisdom. Okay, so yeah, we'll stop here, and just a reminder that your homeworks are due by November 10th. You could submit earlier too, and go. You could just post questions also if you're having some difficulty or errors. And I know some of you have already asked some questions about errors with the assignment, and I have not gotten back to it, but I will get back to it in a few days. Okay. Okay, so thank you all.